much. So welcome to MGM course, and this is the plan. We want to go up to generative adversarial networks. This is perhaps the practical generative modeling that you would like to derive. So far what we did is build intuitions, but we haven't developed any concrete algorithm that works in real life. So this is where we want to go up to real life algorithms. We sometimes do need to go through the intricate details, and this course is about that. It will give you a lot of hand holding about how the ideas get developed, and you go to the actual algorithm. Okay. So before we go there, we will build a little bit, or in some sense we will recall a little bit. These are very basic ideas of analysis, and even if you have not done this, you will learn it immediately, and you can apply these. So we will start with basics of something called mathematical analysis. And these are the basic books on mathematical analysis by Apostol, by Rudin. So this is also called Baby Rudin. And then you also have classical ones by Simons, Topology and Modern Analysis. As I said, these are only for further readings. If you go and become a very serious researcher, then you may have to refer to these books again and again. Very rarely you will need these books in the class. So just for completeness, I'm putting things in record, okay, for those who will be serious researchers in this area. So for you, it's okay to just know what is taught in the class, okay, or in the slides, okay. So no need to worry. So the first thing is infimum. We need this again and again because we are always trying to kind of minimize, maximize, and so on. And infimum is a generalization of minimum. Okay, so it's like infimum always exists, whereas minimum may not exist. Okay, so I will define infimum. So let S be the set of real numbers, and the first thing is that I will define a lower bound. Okay, so if there is a real number b such that x is greater than or equal to b for every x in S, okay, so if there is an element b, that b may not be in the S, okay, that's the important point. So if there is a b for which all the elements of S are greater than or equal to b, then we call b as a lower bound for S, okay. And we say that the set S is bounded below. That's what it means by saying a set is bounded below, okay. So in this case, this set is bounded below by B, okay. We say it's a lower bound because there are many possibilities for lower bound, okay. Yeah, I could have chosen some other B which is less than the current B, and that is also a lower bound. So as you can see, lower bound possibilities are many. If it happens that B is also an element of S, okay, in the definition we never said B has to be an element of S, but if B is an element of S, then we call that element minimum element of S, okay. It will be minimum because all other element in S are greater than or equal to B, and B is in S, so hence it will be flagged as the minimum element, okay, the minimum element. Okay, so a set which with no lower bound, obviously we will call it unbounded below. Then in that case, if there is B, then we call it bounded below. If there is no such B, then we call it unbounded below. So as an example, you can think of a set of real numbers. So set of real numbers is essentially unbounded below, okay, because there does not exist a valid real number B for which all the numbers, real numbers, are larger, okay. So it's so real number is a set which is unbounded below. In fact, it's also unbounded above. So we will go to the counterpart supremum, okay. And then finally we define infimum, which is usually denoted by inf. So when you read papers, you will see this inf of a set, and this is defined to be greatest of all the lower bounds. Okay, as I said, lower bound, there are many possibilities. You choose the one which is the greatest of all the lower bounds, then you call it infimum, okay. So infimum is defined as greatest of all lower bound, and then same thing we can do it for supremum. Wherever you had lower, you change it to upper. Okay, so if there exists a real number b such that all elements x is less than or equal to b, then b is a upper bound. Okay, and then we say that s is bounded above by b. We say a upper bound because there could be many. If b happens to be also element of s, then we call it a maximum element of s, and if there is no such upper bound, then we say that the set s is unbounded above. And similarly, finally, we define supremum of a set is the least of all the upper bounds. So you have many upper bounds, but you have to choose the least of those. Okay. So least of all the upper bounds will be the supremum. So we have defined supremum. Now we define very basic topology. So the concept of open set. To define a concept of an open set, I will define something called interior point of a set. Okay, so an element x in the set C, it could be high dimensional Rn, is called interior point of C if there exists an epsilon greater than 0 for which this ball, so as you can see, this is a ball around C. Okay, you are collecting set of all y which are at epsilon distance from x. So this and this is a 2 norm, so it is the usual ball. Okay, around ball, around n dimensional ball around the center x. Okay, and this is a subset of C. Okay, so this is the definition of interior point. Okay, so do you get it? If you can take some time to see, a point x of a set is called interior point if there exists an epsilon greater than 0 for which I can get an epsilon ball which is inside the set C. Okay, then I call the element x as an interior point. Okay, so the geometrical idea behind this is that x is somewhere inside the set so that I can draw a ball. There is enough distance from the boundary so that I can draw a ball, and the whole ball, you see, the whole ball is a subset of C. It's inside the set C. Okay, that's the concept of interior point. That is, in words, there exists a epsilon radius ball centered at x that lies entirely in C. Then you declare that center x to be interior point. Okay, so set of all points interior to C is called interior of C. So if you can pick all the points of the set C, for which you can always draw a ball, and so and this ball could be however small. Okay, that's, you have a liberty to choose this epsilon. Okay, no, epsilon is something you decide. Okay, however small, it doesn't matter. Okay, so if you can you can go and check for all points of the set C and check whether there is an interior. Can I draw however small ball, and so that it's completely inside C? Go to another point and check epsilon ball and see if the whole ball is completely inside C. So you will get a collection of all the interior points. Okay, now the set C will be declared an open set if the interior of C happens to be the whole set C. Okay, so so that's the definition of meaning all its points are interior points. Okay, that's more or less what it says. A set C is an open set if all points happen to be interior point. This denotes interior of C, interior points of C, and that is nothing but whole of C. Okay, that's the definition of open set. That is, in other words, a set is open if all its points are interior points, and we can define closed very easily now. So the set C is closed if its complement is open. Okay, set C is closed if its complement is open. So when you read some papers, you will see this. They say, let us assume the set is closed and so on. Let us say the gradients are defined in an open neighborhood. So these things are usually there in the papers. Okay, if you see top conferences papers where they are proving some results, so these things are there. And then we can also define a limit point of a set. A limit point of a set is that when you take an epsilon ball, so B sub epsilon L means that it's an epsilon ball centered at L. Okay, the point L, epsilon ball, and if you intersect with S, then it's non-empty. Okay, so so it means that whenever I take a epsilon ball, I always get whenever I draw an epsilon ball around L, and if I intersect with a given set, it's always non-empty. Okay. However small the ball is, okay, that's the point here. However small the ball you take around L, you intersect, it's always non-empty. So a basic intuition behind L is that around L there are many dense points of the set, so that however small you take the ball, it somehow always intersects. Okay, so take for example real line. So if you take a real line and then if you so in a line there the ball is like a segment, open interval, right? So if you take, let us say 0.5, so 0.5 is a limit point, because however small ball I take, if I intersect with the set real, I always get something non-empty. Okay, so it always intersects. Okay, so B epsilon at 0.5, which will be however small interval I take around center at 0.5, it will always intersect. So 0.5 is a limit point of a real number, set of real numbers. In fact, all the points happen to be limit points of a real line, because you can do this for any arbitrary point. Okay, that's the idea of limit point. But there may be cases where points may not be limit points, because if they are like this, but then here they become dense. Okay, so there are cases where it becomes very, so your L could be here. So here again, however small you do, but these guys won't intersect. Okay, because here these guys they don't intersect with the other elements. Okay, so the limit point is like point where elements are getting denser and denser. Okay, and this could be useful in proving convergence and things like that. Okay, so when a point is converging to a point, sequential convergence, if you use some iterative method, then iterative methods usually we expect that it will converge to some point where it will be some kind of a limit point. Okay, so you do this in sequences, convergence of sequences, all this, right? In whatever we do, we always deal with iterative methods. So iterative method produces iterates x1, x2, x3, x4, and so on. Okay, and they are converging to a solution, right? Okay, so we have a concept of a limit point, and closure of a set C, CLC, is the set C with all its limit point. So if I want to make a closure of a set C, then I will put all the limit points there. Okay, which is missing right now, because it may happen that the limit point is outside the set. It can happen, right? So you take an open interval 1, 2. So this is an open interval. Okay, so open interval 1, 2, 1 and 2 are not there in this set. Okay, so S open 1, 2. 1 and 2 are not the element of S. That's the definition of open interval. But 1 and 2 are still limit points. Okay, so and all other points in between 1 and 2 are limit points because of the denseness of the interval. But the only difficulty is here, 1 and 2 being the limit point are not part of the set. So if I have to do a closure of S, then I will add 1 and 2, because those are the only limit points missing, and then it becomes a closed 1, 2. Okay, so closure of this set S becomes closed interval 1, 2. Okay, so these ideas are very intuitive, no big deal. Then we can also think about boundary of a set C. Okay, so boundary, if you don't like this way of definition, there is another way to define, or maybe I will illustrate this in the next slide. Boundary is like that point where wherever you take a ball, you get that point from the set and also from its complement. Okay, those points are defined to be boundary. Okay, because whenever I take a ball, there exists at least some intersection with the set as well as the outside set. Okay, the complement set. Okay, so we can visualize this these things with a figure. X is an interior point because I could find a ball of epsilon radius, however small, it doesn't matter, so that the whole ball is inside the set S. So S is interior point here. Y is a boundary point because whenever I take any ball, okay, whenever I take, however, any ball, it always intersects the S as well as the S complement. Okay, so that's a very intuitive way to define to understand boundary points and so on. Okay, so here X is the interior point, Y is the boundary point. Okay. Okay. So you can do these small examples just to get used to these things. Okay. So find the interior of the following sets as a subset of R. One thing to remember I mentioned here is that that these are all relative concepts. Okay. So which as a subset of which set, when it's important to understand as a subset of which set you are talking about. Okay. So these are because the balls that you will take will be with respect to the parent set. If I change R to something else, then there's some maybe interior points may change. Okay, so because the balls that you're taking are with respect to some parent set. So in this case, our parent set is R, and these are seen as a subset. Now here you have to find the interior points of the following set. So this is closed interval -1, 1, right? So what is the interior point? What are the interior points of the closed set -1, -1 to 1, right? So which are the points around which you can always find a ball which is completely inside S, okay, and these balls are in R. Okay, so which points you think are interior points? Open -1, 1. Okay, so this is interior points, interior of S is open -1, 1. Now with our definition of the open set, is this set now open? We said for open set interior of S is S itself, right? But this is not happening here, right? So we could actually also conclude that this is not an open set because the interior of the set is not matching with the original set S. Okay, so basically all the points here are the interior points of S. -1 and 1 are not the interior point because you cannot find a ball around -1 or 1 so that the whole ball is inside, because some part will be outside, right? Whether it's -1, then the left part will be outside, some part of the ball, left half of the ball will be outside, and in this case 1, right half of the ball will be outside. Okay, so hence -1 and 1 are not interior points. Similarly, you can think of this, it's slightly more involved maybe, but very slightly. So 1 over n, so this is a set S that takes value, let's say n is natural numbers, it starts from 1, so this is 1 to 1, 1 over 1, 1 over 2, 1 over 3, ... and it just keeps going, but the natural numbers are valid numbers. Infinity is not included, so you cannot say for sure that 0 is there. 0 is not there in the set because infinity is not a valid natural number. Okay, so this is your set. We know that it's going to 0, but it does not take 0 value because 0 value will be attained at infinity. Infinity is not part of the natural number. So then you have to find out the interior of this set. So which are the points here around which if you take a ball, however small ball you are allowed, the whole ball is inside S. These balls are balls of R. Okay, this is lying as a subset of R. That's important. Okay, you change the parent set R and it may become open. Okay, so it depends where you're looking for. So what do you think? Here, does there exist any element that is part of S around which if I take any epsilon ball in R, all the elements of the ball are subset? It doesn't exist, right? Do you agree with that? It does not exist, right? So you cannot pick any point because these are kind of discrete points. Okay, so any point you think of, however small you take, because epsilon cannot be, because it cannot be just a point. It has to be some ball with some finite radius. Okay, I mean some non-zero radius. So moment you have, however small ball you pick, there is always infinitely many points from the real number which is not part of the set. Okay, in the neighborhood of 1/3 there are so many real numbers which is not part of S, so it cannot be a subset of S. Okay, so here there are no interior points. The interior points are none here in this case. Okay, So this way you may try some other exercises. I don't want to go too much into this. As long as you just have basic idea, it's fine. Okay, we are not going to use too much of these things. So you can find a closure. Okay, and you may also find a boundary. So what are the points here around which whenever you take any ball, you always have points from the set as well as from the complement. Okay, so what do you think in this case? It's easy. Boundary points. What are the boundary points here? -1 x. So you have to, which element, I mean the boundary point may not be part of the set, I'm saying. Okay, so you are allowed to have points which are not here. So which are in this case? -1 1, right? So -1 1, although not part of the set, it can be a boundary point. So wherever I take a however small epsilon ball around -1, it will always intersect with the set open interval -1 1 as well as the complement. Okay, so -1 1 are that, but any point that is you have inside, okay, there will exist a ball however small, just even if you go just slightly inside, you have a leverage to make a small enough ball so that it's completely inside. Okay, so those points will not be boundary. Okay, any point who is just inside -1 1 can never be boundary, because you will always find a small enough ball. Now this is interesting. The set Q, the set of rational numbers, what are the boundary points of set of rational numbers, right? So you may try this. In the interest of time, I mean just go over this, and then you can also try to identify which of these are open sets and which of these are closed sets. Okay, so open sets, as we said, open sets are sets for which all the points are interior points. So in this case, you can think set of integers are all the points of set of integers interior points as a subset of R. Okay, so the answer is no, because I can never find a however small ball such that it's completely inside the set of integers. So it's not possible. So in this we have already seen. Similarly, you can try slightly more interesting ones. You may try these examples as an exercise. One more thing we may need is a concept of something called lower semi-continuity. So we can relax continuity sometimes and still it's good enough. Okay, so there are two variants: lower semi-continuity, upper semi-continuity, and these are slight relaxation of continuity. Okay, so again, these are definitions that we just have to know. Okay, so if I have to, both are equivalent, but this may be more intuitive. Okay, so let us see what this says. A function f from x to r. So I'm also, r bar here means extended real system. The extended real system means now it also includes -infinity and infinity. Okay, so real number as such don't assume infinity or -infinity, but we can build some extended real system. So what it says is that a function is lower semi-continuous at point x naught in the domain if for every real y which is less than fx naught there exists a neighborhood, means the ball, neighborhood means ball in analysis, neighborhood u of x naught such that fx is greater than y for all x in that neighborhood. Okay, so this is what you can imagine. So you have to pick for every real y which is less than fx naught, there will always exist a ball around x naught which is for which fx is greater than y. So if we see for some examples, these are some of the examples. This is Heaviside function which is 0 if x less than 0, and it is 1 if x greater than equal to 0. There is a non-example here. Again, I'm leaving these things out. If you have a basic idea, it's fine. You don't really need to. Then we can also define upper semi-continuous. But one, I would say that a function is upper semi-continuous if the negative is lower semi-continuous. So essentially you can forget about upper semi-continuity. As long as you understand lower semi-continuity, it's fine. Okay, you just take the negative of that and prove that it's lower semi-continuous, then the original function is upper semi-continuous. So again, example here, and this is an example of a function which is lower semi-continuous but not upper semi-continuous. Okay, so basically what this theorem says is this is lower semi-continuous. So we have to pick a, so this is our x naught, right? And this is our fx naught. So in the definition, what did it say? For any y less than fx naught, so we can pick some y here which is less than fx naught, which is here. So we can pick some y here which is less than fx naught, and we can trace. So we can trace the definition. Yeah. So y less than fx naught, for every real y less than fx naught, there exists a neighborhood u of x naught. Okay, there exists a neighborhood u of x naught such that fx is greater than y. Okay, so such that fx is greater than y for all x in the neighborhood. So can we create such neighborhood? Okay, whenever y is less than fx naught, can we create a neighborhood around x naught such that fx is greater than y? So this is our fx naught. This is fx naught. So I guess I will take a y which is slightly like here. Okay, so so this does not recognize my hand, so I don't have to put my hand there. So this is our y. This is where it intersects, and then it was about the points are being greater than y, right. So it was about point being greater than y. So then it's fine. Then it means that I will pick a very close one like this, and then these guys are my fy. So these points are certainly greater than y. Okay. It's a little bit tricky definition, but I hope you get the point. So what did the definition say? For any y less than fx naught, so fx naught is somewhere here, again this is slightly offset, then I can create a ball around x such that these guys are above y, fx is greater than y, above y. Okay, so that's the definition of semi-continuity. Okay, so as you can see, this lower semi-continuity allows you to work with not necessarily continuous functions. This is slight generalization of continuity. Okay, so you can state results with lower semi-continuity rather than saying it's continuous. Okay, so with this in picture, we and then upper semi-continuity, just take the negative and then work with the same idea. Okay, so then we have we recall. I think most of you already know what distance means or metric means, or so metric in general is some kind of a distance, but here the distance concept is like generalized. So if D has to be a metric or a value distance, then it should be non-negative for any x and y, and it should be 0 only if x is equal to y. It should be symmetric in the sense that x, y should be same as y, x distance. It should satisfy triangle inequality, so meaning that if there is any point y other than x and z, then the distance of x and z is less than or equal to distance of xy plus distance of yz. Okay, so this is triangle, the usual triangle inequality we have. And we can define a space, metric space, to be a space with the set X, and D is some metric that satisfies these three properties. Then we call it a metric space. So examples of metric space are real numbers with the metric defined to be absolute difference between 2 points is a metric space, because this defines a metric. And in R2, the usual 2 norm is a valid distance. Okay. And in the set of integers, we can define again same distance like in real number, the absolute difference. Okay. Okay. And then we need a little bit of convex analysis. Actually, we did convex analysis a little bit already, so I will go through them very quickly. Where do we need convex analysis in generative modeling? Okay, we need convex analysis in generative modeling to discover more general divergences. This more general divergences allows us to see generative modeling for more generic view, in the sense that I can play around with those generic divergences to discover more interesting divergences. So for example, if you see negative of the log in the KL divergence, so KL divergence term involves log. So if you look at the negative of the log, negative of log is a convex function. Okay, and then one possibility is could you have replaced negative of the log with something more general convex function? Okay, that's the idea of F divergence. So we will come to that today. Conjugate functions also are convex functions. So we will see that what is conjugate of a function. So given a function, I can compute a conjugate, and that's always convex. So then this idea will lead us to deriving min-max formulation for GANs. And in general, convexity is also useful when we use optimal transport based ideas for generation. Okay, so that's when we focus on the earth mover distance. That's another divergence between two probability distributions. So this is also we will see where where we will employ a regularity term which will lead to strong convexity, and again here convexity will help us so that we will use some existing algorithms for solving such problems. So there again, as to make a problem well posed, you may add a regularizer that makes everything convex, and then you are good to go with the existing algorithms. In general, non-convex problems are hard to deal with because they are not well posed, okay, because they can have many minima, local minima. Your algorithm can get stuck in any of these. So in the theory of min-max solvers, so when we consider GAN, that we will see it's a min-max problem. It's a min-max optimization problem. And again, when I'm discussing solvers, so once the problem is formulated, the modeling is done in terms of min-max. Again, I have to solve this min-max problem. So when I'm discovering solvers for min-max problem, again, the ideas of convex, concave, and all this is useful. So that's why we study convex analysis a little bit. For more references on this, one can always look into this. But as I said, this class is completely self-contained. You don't have to really open any book if you really understand what I teach in class. But if you are a researcher, then you are invited to go and read these books in more detail. The first two are basic. These are taught in UG course, and if you take those electives, so this is pretty much okay to handle. The next one is a little bit advanced one. So this is upper graduate course, and the idea here is variational analysis. So basically, the min-max problem and all this could be generally seen in terms of something called variational inequality. Okay, so these are way more advanced. Okay, regarding the third one, for example, the min-max problem that we see, the solvers for those could be unified with these ideas of these Mokhtari 2020 paper, where they do some analysis of the solvers for generative adversarial networks, or the min-max problem in general, and they see those problems as variational inequality. Okay, so as I said, some of the things I point out are advanced. You don't have to bother about that in this course right now. So we have already discussed convex set. In convex analysis, the basic thing is convex set. So convex set is a set where I take any two arbitrary points, and if I join a line, then the whole line is inside the set. So this is the parametric equation of a line, and to define it to be a line segment, theta must be between 0 and 1, obviously, and theta should be greater than or equal to. So in this case, it's obviously implied that theta is greater than or equal to 0 is already defined. But in general, if you take a convex combination, then you can do a convex combination of several points in the set. Then we call it convex combination. Just like linear combinations in linear algebra, you can do convex combination, but this is a special case of linear combination because the scalars that you have are such that they sum to 1 and they are necessarily positive, which is not the case in linear combination. So if a set, in the set, if you can take multiple points, do a convex combination, then in a convex set, the point necessarily lies in the set. Okay, just like in a vector space, if I take bunch of points, I do a linear combination, the point must lie in the space if it is a vector space. So these ideas just extend. Okay. Certain operations preserve convexity. So if you have an affine, if you have a linear transform, and if you apply this on a set, then it remains convex. So we have seen this. If you have an affine transform, linear transform, if you do inverse image of a convex set, then also it remains convex. Okay, so these are basic results. I'll just go through this quickly. If you multiply the convex set with some scalar, it still remains a convex set. If you translate the convex set by a number, it still remains a convex set. So all these are very intuitive also. Okay, if you just translate, it doesn't destroy the geometry. Okay, if you just if you also do scalar multiple will kind of like elongate or something, but still it doesn't destroy. Okay, so you can take two arbitrary points from alpha s, and theta of x plus 1 minus theta of y, you will check that it is also of the form sum alpha x. Okay, so these things all you can prove this. But you can just remember, okay, even if you don't prove. And then convex function. So we have defined convex function as well in the previous class, so we can just go through this very quickly. What this inequality says is that the line joining, let's say, function values fx and fy, if you see them as a point, right? So this is above the function values taken between x and y. Okay, so you can just remember this like this. So this is always the case. Okay, so whenever I take any 2 points on the curve, and if I graph of the function, if I join them, then those values are always above the function values. So this is given by the function value, right? X and y are in the domain, so you are somewhere here, and theta x plus 1 minus theta y is the segment between x and y, and those function values will be f of theta x 1 minus theta y. So these are the curve values, and this is theta is outside, right? So then it is like theta times fx and 1 minus theta times fy. This means that this is the line joining fx and fy. So intuitively, convex functions are easy to understand. We can also call it to be strictly convex if this inequality is strict, and we can also define concave functions if the negative of the function is convex. Okay, so you can try all this. We have done some of this already in the class. So how do you check whether a function is convex? One thing is to go with the original definition, and there are simplified ways to check if the function happens to be differentiable. Then using gradient also, by satisfying this inequality, you may prove that some of these are convex. And if it happens that it is twice differentiable, then it's even simpler in quotes, meaning if you can prove that this is a positive definite matrix. Okay, so it may not be easy sometimes, but sometimes it's way easier. Okay, because if f is a n variable function, then this if you take the gradient first time, it becomes a vector. If you take gradient one more time, then it becomes a matrix. And greater than equal to 0 for a matrix means that it's a positive definite in this case. It doesn't mean that each entry is greater than 0, obviously. Positive definiteness means that you can say that the eigenvalues are greater than 0 now. Okay. In the simpler case, you are familiar with this calculus result, that if the f double prime is greater than equal to 0, in that case we can say that it's convex. And then again, you can try this as an exercise. These things are better done in exercises. These are simple results. And if you look into the quadratic case, this is a quadratic function, then in that case, if you take double derivative, if you take first derivative, then this r will go away, you will have q, and then you have half goes away, because you have like square terms, x square type terms. So so what you will be left with the first gradient will be px plus q, and if you take one more derivative, you will be left with only p. Okay, so you can play around with this multivariable derivative and so on. Okay, but essentially I don't think we will be doing this by hand. All this for this there are libraries, but it's good to understand these concepts. Okay, so what is gradient, what is Hessian? So in this case, for this guy to be convex, now the second derivative gives us p. Now then from second derivative test, p must be positive definite. Okay, for this to be quadratic function to be convex. And then there is a concept of epigraph. We are only picking things that are strictly needed. I guess this is this and conjugate function is the concepts that we will need in this course from convex analysis. So another thing is epigraph. So epigraph of a function is the region above the graph of the function. Okay, and so this shaded region. So this is the curve graph of the function, and anything above this is called epigraph. Okay, so epigraph allows you to interpret convex function with convex set. So now you can say that a function f is convex if and only if the epigraph of f is a convex set. Okay, so there is a difference. Okay, set, convex set, and convex function. So in this case, epigraph somehow allows you to relate. So f is convex if and only if the region above the graph of f happens to be a convex set. Okay, and this is if and only if. Okay, so you can do it either way. And what we need for our case is that when do we define a function to be closed? Okay, one thing we have seen is open set and closed set. So then we can also define a function to be closed if its epigraph is a closed set. Okay, so we have defined open sets and closed sets. Now we declare a function to be closed if its epigraph is a closed set. Okay, meaning this guy shaded area should be a closed set. Okay, or in other words, its complement must be open. Okay, so these are the things we will need, and the last ingredient we need more or less for the whole course from the convex analysis part is something called conjugate function. So conjugate function is a function that is created from the existing function f. So f star is defined to be conjugate of the given function f, and this is defined like this. Okay, it looks a little bit too much, but we will do one or two example and it will be very clear. Okay, conjugates could also be seen as a kind of dual. Okay, it's like going from time domain to frequency domain. So in this case, the way I like to see this is that going from domains to the slope domains. Okay, so there is a geometric interpretation for this. You may follow my maybe the YouTube thing, I give optimization course, and I spend half of the class on this. So you may refer to that. It's like I can see the function as slopes. Okay, so slopes are my it's kind of, I'm going to a new variable which is the slope domain, going from the domain which are defined by x and f of x, but I can visualize functions as approximated by slopes. Okay, vaguely. Okay, the more precise way it's explained, because there is a supremum also and so on. Okay, so you may have a look, but from our point of view, it's very not. It's okay for us to calculate. Okay, so how do we compute conjugate, right? That's the main thing, right? So we know that it's defined like this. Basically, we have to take supremum of this quantity y transpose x minus fx. Okay, and we have to maximize this over x. Okay. So the domain of the conjugate function consists of y, for which this supremum is finite. This should be sup. Okay, so supremum is finite. That is, the difference is bounded above. In fact, that is exactly what we need. So for every y that you pick, okay, I'm going to define this f star, right? So what I will do is that I will pick a y, okay, and then check for which x it is bounded above. Okay, so because if it's not unbounded above, then that point cannot be in the domain of f, because domain of f are only those points for which a function takes varied values. So in fact, this is the very basic idea that you have to keep in mind. Assume that y is fixed, and then go here and check for which x it becomes unbounded. Okay, and so that will give you an idea of which x to choose in that case. Okay, or which x to discard. Okay, so we'll do an example shortly. So you can just keep the definition in mind, and then we will try to. So what is important here to note is that f star is always a convex function, regardless of f is convex or not. This is interesting because f can be non-convex, but somehow if I can work with the conjugate, it's always convex. Okay, and the reason is because of this supremum term. Okay, and so f star is convex because it is a pointwise supremum of the family of convex functions. Okay, because this is like a supremum over all the convex functions. Okay, so and this is convex because this will be seen as a function of y. Okay, because for each x I get y transpose x minus fx. For another x, I see y transpose x minus fx, and this is supremum of all those functions for different x. But each of these are convex functions, right? So that's why it's because supremum of a convex function is maximum if you take of various convex function, it remains convex. Okay, so if you have convex function like that, you have convex function like that. These are the convex functions you have, right? So if I have to take the supremum, okay, so all these are like well defined. So this guy is the highest values, and from this point this guy is the highest value. Okay, so supremum is this guy, which is still convex. So supremum of set of convex function is convex. In our case, these are the set of actually linear in y. So I'm taking supremum for all x. So pick one x, it's some linear function in y. Pick another x, it's linear, because fx becomes a constant, right? And x becomes a constant. Once x is fixed, x is a number, fx is a number. Okay, so this is only a function of y. So in this case, these are essentially linear functions. So if we see the intuition behind this, then conjugate is a convex function because these guys are linear, right? So it could be this for some x1, this could be this for some x2, this could be this for some x3, this could be this for some x4, and these are all this is x1, right? So this is like y transpose x1 minus fx1. So this is a function of y, and this is linear. Obviously this is of the form y transpose x. So this is a linear function. So if I take supremum, obviously this is a convex function. You can see this is a ball shaped. So this is a convex function. That's why conjugates are convex function regardless of what f is. Okay, so that's an intuition behind convex, but if you can just remember, it's fine. Okay, so f star is convex regardless of whether f is convex or not. for fixed y, find x for which the supremum is achieved. So that's the way to calculate. So now let us look into some examples. So given a function like this, ax plus b, what is the conjugate? Okay, negative logarithm. So given a function like this, minus log x, what is the conjugate? So this could be useful in the KL divergence when we will look at the conjugate. Similarly, exponential, fx is e to the x, what is the conjugate, and so on. So you can you may go ahead and see some examples in. I will do one or two here, but if you want to see more, then you can see page 91 of the book. It's an open PDF. Okay, so let us try and practice some examples. So if I have ax plus b, okay, and I am supposed to find the conjugate of this. So to find the conjugate of this, I construct. I look at the supremum. So let us look at the supremum values. So let us write down the expression for the conjugate, right? So f star y is supremum over x of yx minus fx. Okay. So our fx is ax plus b, right? So our fx is ax plus b. So I'm going to put it here. So minus ax minus b. Okay. So I substituted the fx. Now our because we want to define a function, right? So I want to, for every input, I want to say whether I can get a valid output. So I will take some y. So in some sense y is fixed. Let us say in your mind you can say y is fixed. So y is fixed, and now I'm looking at what are the x for which this doesn't blow up. Okay, where the supremum is valid. So when do you think this guy, for a fixed y, okay, for a fixed y, when does this guy necessarily blow up for some values of x? Okay? That's the question, right? So does this necessarily go to infinity for a fixed y? Can I make it go to infinity? That's what I'm saying, right? So do you have a leverage with x that will necessarily make it go to infinity by changing x, right? Obviously you have leverage over x, right? So is it possible that I choose x in a way that for a fixed y it does go to infinity? You can assume something b is a constant, a is a constant, right?
Proportional to x, right? As x goes to infinity, this
Yeah.
equation will also.
So as x goes to infinity,
The whole expression will also go.
but it will also kind of depend on a and the y that I choose, right? I mean it may.
If y is
It may also go to minus infinity. In minus infinity, we don't want anyway. We are always looking at the plus values, right? Y is a constant. So you can increase x.
it's only defined for y equal to a.
Yeah. So or what if, because I want to take it to plus infinity, right? Our goal is to see whether it goes to plus infinity, right? So because if a is positive, this guy is negative, right? And also depends on y was taken to be positive or negative, whatever. Okay, so we could have simplified this like this, y minus a x minus b. Okay, so that we focus on this. So in that case, right, we can make it go to infinity, right? We can make it go to infinity in all cases, unless, yeah. But even if y minus a is not positive, x I can take negative, still it goes to plus. Yeah, actually in either case we will make it plus infinity, right? So now tell me, there is a case where it will not go to infinity. Which one? Y is equal to a, exactly. So y equals to a, that's the whole x term we want to vanish, because that is the troublesome guy, right? So there is a possibility for a y where f star is defined and it is minus b. Okay, in that case y is a. If y is not a, it will surely go to infinity. So that is how we find conjugate, actually just by looking at this x and which cases it goes to infinity and the cases where it doesn't. Okay, so in this case f star y is defined to be, so basically the y f star y is minus b, and where domain of f star is only a. So basically y takes only a values. In any other value of y, the supremum goes away. the moment y is a, obviously this guy goes away, so there is nothing left with x, so supremum is just this constant minus b is left out, so that's minus b there. So that is how actually conjugates are found, and this is exactly what we did here. And same thing one could do with the log x. So we have minus log x, and then we look at the same term like yx minus fx. So in this case it will be yx or xy, minus minus becomes plus here. So xy plus log x. Okay. So this is this guy is unbounded above if y is greater than or equal to 0. Okay. So you may check this. If y is greater than or equal to 0, it will go to infinity if you do supremum on x, which seems to be correct, because this guy will dominate over log x. If y is greater than or equal to 0, then this guy he will, y is 0, then obviously log x blows up anyway, although it goes slowly, but it does blow up to infinity if x tends to infinity. And whereas if y is strictly positive, then obviously x I can really take very large, and this guy overall completely goes to infinity. So y greater than or equal to 0 is out of the question. Then for other cases, you may take a derivative of this and equate to 0 and see where the supremum will be achieved. Okay. So for the other case, you take the derivative of this with respect to x, obviously, because we are trying to find maxima with respect to x. So then you have y plus 1 over x equals to 0. So you take derivative y plus 1 over x equals to 0. So from here, if we solve for x, then we get it to be minus 1 over y. So for that minus 1 over y, you have the supremum achieved for those y which are less than 0. The supremum is achieved. So you have to put this back in the in this because that's where the supremum is achieved, and the output that you get is the so let me do this quickly. So right now what we found is where the supremum is achieved, and then we have to write down the f star. So f star is in terms of y. So wherever I have x, so y times minus 1 over y times minus 1 over I. So this is where the supremum is achieved. So then I remove the supremum because I know where the supremum is achieved, plus log of minus 1 over y. Now log of minus 1 over y is still well defined because y is negative. Okay, so there is no issue yet. Okay, because it is, and y greater than or equal to 0, we already know that it blows up for sure. So this is well defined. Y less than 0 means this is positive argument for the log, and this guy actually gets cancelled. So this is minus 1 plus log of minus 1 over y. Okay. So again, these are concepts that you learn necessarily when you perhaps go for research and so on, so that you have the pointers like where to look at. But usually for our understanding, we will know a function and we also know the conjugate. We will just pick up those things and proceed. Okay. So okay, and then you can also do this. But okay, one thing is this inequality. It's called Fensel inequality. This says fx plus conjugate of y. Y could be any in the domain, and x could be any in the domain of f. Then it's necessarily greater than or equal to x transpose y. Okay. Again, we just have to remember these results. We are not going for the proofs anyway. So we just have to. But what we really need is conjugate of a conjugate. Okay, that we will use immediately. So the next question is, what happens if you take conjugate of a conjugate like f star star? So what happens in that case, right? So there is a very unique case where f star star is f. Okay, so that happens for certain kind of functions. So if f is convex, okay, that's why we studied convex. Okay, so if f is convex function and f is closed, okay, we just defined f is closed if the epigraph of f is a closed set. So if you know both f is closed and you also know how to verify f is closed by looking at the epigraph, then in that case there is a nice result that f double star is f. That's very interesting. In fact, this is exactly what will be used to derive GAN. Okay, so the conjugate of f is f again. Okay, so if you want to know more pointers about this, you can go and look at the Boyd's book. But as I said, we don't need anything more than the slides. Okay, so now let us get back to the business of generative modeling. We have prepared a little bit that will be needed immediately. So remember KL divergence. Okay, so Kullback-Leibler divergence was proposed in 1951 from the view of information theory, but we are now using its generative modeling as well. It's a divergence. We are not calling it a distance or a metric. We have seen this previously as well, that it is indeed not a metric, and this is defined like this. And I have made this an alert where there is a log here, and we can stare at the log and see why log there, right? So after staring at the log term, what do you suggest? Well, I see negative of the log. Negative of log is convex, so why should I stick with log? Why not use any generic convex function to generalize this scale divergence? Okay. So minus log x is indeed a convex function, we have already seen. So can we use more generic convex function? So that's the idea of f divergence, and that will allow us to derive. So now let us look into also a slight symmetric variance of KL divergence, which is called Jensen-Shannon divergence. Okay, Jensen, we don't say Jensen, we call it Jensen because it's a Danish guy. So the J is pronounced as Y. So Jensen-Shannon divergence, or J's divergence, is a symmetric and smooth variant of KL divergence. So this is defined like this, where you define an M separately, which is half of the P plus Q, okay, the distribution that we want to compare, and that M is used to make KL divergence symmetric. So this is KL divergence PM, but then you also do QM. And this is good because this makes it symmetric. Now if you do QP, due to symmetry, you can say that it's the same term, right? So you can now reverse. It was not true for KL divergence. KL divergence PQ was not necessarily equal to QP. We have shown with some examples, but then this guy fixes that. So it becomes a symmetric variant of KL divergence. So it is bounded. Unlike KL divergence, also we saw in the previous class that KL divergence can become unbounded if a sample is not seen, because you have division by a distribution for which you do the sum during the expectation, and then that term is not there, so divide by 0 happens and you get infinity. This issue is not there in J's divergence, because the division part is the second part M, okay, and which is combining P and Q both, okay. So that way, kind of it gets away with that issue. And then J's divergence is symmetric. Again, from the symmetry, it's more or less clear. J's divergence always takes values greater than or equal to 0, takes values between 0 and 1. And J's divergence is a metric. Okay. So now we would like to go to something called f divergence. Okay. So sometimes we write divergence as expectation, sometimes we write it as integral. Okay, so you could essentially remove the integral and write sum if it's a discrete setting, so it doesn't matter. We use those interchangeably. Expectation for a continuous random variable is given in terms of integral, and for discrete it's written as a sum. So f divergence, we can define it to be if f is convex and if it's lower semi-continuous. Okay, so we have seen what is lower semi-continuous, such that f of 1 is 0. Okay, so basically if this is f, right? So as you can see, f of 1 0 essentially means that if P and Q match, then I want the divergence to be 0. Okay, so if f of 1 is 1, so from here if P becomes Q, then obviously my distance should be 0 because the distributions are same. Okay, so that makes sense. F1 is 0. So we define the f divergence between two distributions with densities P and Q on X as this. Okay, so we use this sub f here, and this is integral form. And in place of there are two changes basically. You see that this is very similar to KL divergence. There was a log there. Okay, but there is one more difference from KL divergence. This guy got below, whereas in KL divergence it was above. Okay, so there are two slight changes, but again KL divergence could be derived as a special case of this by a proper choice of f. Okay, so if you take f to be x log x, for f to be x log x, then this becomes KL divergence. Okay, so f divergence is, there is a slight change, as I said, because in KL divergence this guy remains at the numerator, the guy that you multiply remains at the numerator, so it's like p log p by q. Okay, so there is a slight change here, and log is replaced by something general. Okay, so but with f equals to x times log x, this is indeed KL divergence. Okay, so that's the extension of the KL divergence that we kind of generalize a bit. I will give you all the motivations behind why we are doing all this. Okay, we will go step by step with everything. So okay, so with fx equal to x log x, we have the when I don't use the sub sometimes, then by default I'm saying that these are KL divergence. So here just D means the usual divergence, which is KL divergence in our case. So F divergence becomes KL divergence and so on. And you could also do negative of the log, then you get it reversed for the KL divergence. It is non-negative. It is also easy to prove that the F divergence is non-negative because if you look at the F divergence PQ, so this is nothing but the expectation of this guy with respect to the Q distribution, right? So you remember how the expectation is treated. So this is expectation of the Fx guy with respect to Q. So expectation X with respect to Q of this guy, right? So this is same. Okay, we just wrote this as an expectation, and if we can take F out. Now this is also interesting. This is also related to convexity. There is something called Jensen's inequality, which is very similar to, because of the fact that F is convex. What do we know? Average of the F, theta Fx1 minus theta Fy, is something similar here. Average of the F is greater than or equal to F of the average. Okay, this is actually because of the convexity. So they made an inequality out of that. Okay, so if F is convex, then it satisfies the so-called Jensen's inequality, and this just extends in this case. Okay, so so this is nothing but average of F is greater than or equal to F of average. This always happens for convex functions. Okay, so this is exactly what is Jensen's inequality. You just have to remember the way I said. You don't necessarily have to kind of go too much into this. Ready? Now motivation for KL divergence. Okay, so I have defined F divergence also, and I have replaced the log with slight change by a convex function, and I ended up to F divergence. And one of the things is, like, even why should I look at KL divergence also? Okay, I know that there is extension F divergence, but what is there with KL divergence and how it's related to, let's say, maximum likelihood? So it turns out that KL divergence, if I want to minimize, it's the same as maximum likelihood estimation. Okay, so let us look into this derivation. Okay, so this is KL divergence, dp of p theta. Okay, there are two distributions, p and p theta, and so this is the same guy p theta here, but as you can see, I have added this h of p term. This is entropy term. Okay, so I have added this entropy term. I have added this without changing the minimization problem, because this is a minimization over theta. So I am saying that there is a parameterized distribution p theta. Okay, in maximum likelihood, we pick a parameterized distribution p theta, and we try to see whether how close it is to the original distribution, right? So we are doing that, but here we have KL divergence, and I have artificially introduced HP, because if you see, if you remove HP, this is still the same, and I can do that because p does not depend on theta. So the argument where where this minima is achieved is not going to change, because p is independent of theta. Okay, so minima is not going to change. By doing this, I have done it for purpose. It will cancel out the p, and hence everything will remain in the log p theta. Okay, so this is my HP, and then I get to this step. Okay, so why I get to this step? So we have this KL divergence term that we may write out, and let us do this quick derivation. We have the entropy term. So entropy term is minus log of p. Okay, the HP is defined as minus log p. So let us do this very quickly here. This is simple derivation, but we can do it quickly to get to the next step, the fourth equation. So HP is minus log of px, right? So we have arg min. HP is minus log. And plus the KL divergence, right? So the KL divergence is basically the expectation of x of p, and so I'm supposed to cancel out p. I'm supposed to cancel out p. That's right. So this is expectation of p log of px by p theta, right? So log of, okay, let's see, it will work out, px log of, right? So this is our KL divergence. This our second term is our dp p theta, and the first term is the entropy term h of p, and I will reverse this guy. And actually this is also expectation over, because entropy is a expectation of the log of So this is expectation over x and like this. Okay. So entropy is expectation of the negative of the log. Okay. So these expectation being linear, I can combine them, but this guy is negative. So again, expectation being linear, the constant comes out, and then my plan is to cancel out p and combine them. Obviously, if I reverse this guy, I will get a negative here. So I will see a p down, and the negative here becomes plus, a negative common, and this p gets cancelled. That's my plan. Okay. So this is arg min of theta, and so assume that I took a negative and reversed it. Okay. So I will try to do this in one step now. Okay. So minus of expectation, and then log of p theta x. Okay, that's the point, right? We reversed it. P theta x by px, and I combine this guy, right? So this is also log, right? So they get multiplied, and then we have px. So this is the whole thing we wrote, right? So I did a two-step. Reversed it, I got the negative. Negative of expectation is taken common because expectation is linear, and the log of a plus b is log a times b. So that's what I did. Log of a b times a, negative expectation out, and that was the trick, right? That was the trick to cancel out this guy. So what we are left with is arg min over theta of minus expectation xp, and this is log of p theta x, right? Now is this maximum likelihood, or it is not maximum? It's minimum, right? But there is a negative, right? So if I'm doing minimization of negative, I can make it maximization of the negative of that. So if you take one more negative, and I'm allowed to write it as arg max. Okay, so this becomes arg max, and negative goes away, and this is your familiar maximum likelihood that we spent so much time on, right? So this is log likelihood. Okay, so this is maximum log likelihood MLE with the log likelihood function. So as you can see, what did we prove? We started with KL divergence. We said, what does it mean when I am trying to minimize two distributions with the KL divergence? It turns out you are doing nothing but just trying to fit p theta on the samples coming from the original distribution p. So basically what I ended up proving is that KL divergence is same as maximum likelihood estimate. Interesting, right? So we started with this intuition before, right? That I can pick some samples from the bag, or and then I can build a parametric function p theta, and I fit this parametric distribution p theta, that is find the optimal theta, and that's the distribution that represents the original distribution or approximates, right? So it turns out working with KL divergence is similar to MLE estimate. Okay, but then you can say, why do we go for KL divergence, right? So I will come to that. This will allow us so-called variational lower bound and things like that. So for the moment, this is already like, okay. So I have just described what we did. There is nothing more to say here. I have already said in words. Okay, so we have KL divergence same as so. Why KL being equal to MLE is good? Okay, so we have seen in statistical inference, there were some slides there, that MLE estimator is a consistent estimator. So let us see what it means, right? So there are basic things like, okay, KL is non-negative, that we already seen. KL is equivalent to maximum likelihood estimate that we just proved in the previous. What is new here is this MLE estimator. So our estimator is what? What we are saying is that I want to actually estimate log p theta x, and I can do it with a random sample. So I can take a sample of size n, and I can take an average of these, right? So then this is my MLE estimator. Okay, so this is maximum likelihood estimator, and this is as n tends to infinity, as I take more and more samples and then construct this estimator via the random samples, and I take a usual average. This is the sample mean. What are you trying to do here? You're trying to approximate log p theta x. That's your goal. Okay, what is the nice log p theta x? How can you do that? You can do it only with the samples. That's the only thing you have in hand. So what it is saying is that as your sample size is growing, the average of this likelihood function that you get is actually as if you took average of these from the original distribution. Okay, so this is like the sample average. Sample mean is the true mean as the n size is growing. So if you have seen from the statistical inference class, then we had this. We can call this as a theta hat, as an estimator that depends on n. So we call theta hat a consistent estimator if theta hat n goes to theta. In our case, theta is log p theta that we want to estimate. Okay, the true expected value of log p theta in the true distribution p, we don't know. So this is like hypothetical, right? But what this is saying is that if you do it like a usual average that we do, then it is indeed as if like your estimates are from the original distribution. Okay, so this is a good thing about MLE estimator. Okay, this is in general about MLE estimators. Okay, and I know that KL divergence is equivalent to MLE estimates. So KL divergence, whatever is good for MLE is good for KL divergence. Okay, so if KL divergence, KL divergence MLE and MLE estimates are consistent, then why don't we use MLE? So why did we bring in KL divergence, right? So that's the main topic, right? So let us assume that we want to approximate the MLE, the log likelihood via the samples. Okay, so we want to approximate it via sample average, and that's what we have. What is the problem here, right? So our main thing is when we are saying we have maximum likelihood estimate, then what is the problem that prevents us from working with maximum likelihood estimates? Okay, so the answer is right here, right? Can you really compute these guys p theta xi? Because this is a joint distribution, right? Your xi is a full image, a vector of pixels. Okay, and again, what will you do? It is only theoretical, right? P theta xi, where xi is a one big vector. How will you compute that, right? How will you compute? Again, independence assumptions, no, that's not a good idea. We have already seen. That's why we built these intuitions before, right? We cannot assume that the joint distribution is product of the individual. That is too bad. It's not like a coin toss, right? Again, if you go for the chain rule, then again chain rule we have conditionals, and more conditional is again not tractable. So either way we are still stuck, right? We even though we can do these Monte Carlo estimates and things like that, Monte Carlo estimates is just like estimating something via samples. Okay, so in this case we are estimating what could be our log likelihood via the samples. Okay, but the problem is, again, this is joint distribution, right? So that's the problem. So for higher dimensional problem, xi could be a very big vector. Okay, so 64 times 64 length, and pxi is a joint probability density. Again, okay, so we cannot do independence assumptions because in the case of pixels, conditional dependencies exist between pixels, and using chain rule. Also, it's not tractable. We have seen this in assignment already in the previous lecture as well. So although theoretically MLE estimates are there and they are consistent estimators, but the joint probability distributions that you are going to compute with your parametric distribution is still not tractable. That's the whole idea. Okay, so so how does F divergence help? Okay, so we have introduced so many things, right? So many things are going on right now. So we have started with KL divergence, then we said KL divergence is same as maximum likelihood. We said maximum likelihood has nice features. But then when we look into the likelihood function, it's the same old problem that we have seen in the previous class. So now we want to get something from F divergence. Okay, so let us see this. What does F divergence do? We will prove this perhaps in the next class, but what we will derive is this. The KL divergence, or not KL, in this case is F divergence. In fact, this comes via F divergence. So that's why we introduce this, is lower bounded by this guy. Okay, so if you don't understand this, this is fine, and you can also see the F star conjugate there. Okay, so what this says is that it's lower bounded by expectation of some operator Tx, okay, where x is coming from P, and minus expectation of F star. So this is the conjugate of the F. So whatever F you are using in the F divergence, that F and the conjugate of that times Tx. So what we are saying now is that the KL divergence is equivalent to maximum likelihood, but then I cannot compute, it's not tractable, but can we do some kind of lower bound? can we have a good lower bound? Okay, that's why we need maths, right? So that is, we would settle for some good lower bound. Okay, you can replace f by the KL divergence, but the derivation comes via f. Okay, and then you can make it kind of special case, okay, with the choice of f, but we get this bound in general. Okay, so overall idea is that this divergence measures, we want to have a lower bound, and lower bounds are tractable. Okay, so that's why we call it lower bounds. Okay, and these lower bounds will show up also in the diffusion models. We call it elbow. Okay, it's evidence lower bounds. Okay, that's the term that's given. So you are looking for lower bounds of this which are tractable in practice. Okay, so that's why we need maths, knowing how to make such lower bounds, right? And we will learn, we exactly learn these things in this course, how to make things tractable, right? So f star is our something that we already defined. I just put it here. It's conjugate function, and this result, this is a specific case where I choose any t, then I get a lower bound. But if you could make a supremum of this, if you can maximize this over the t, then you get exactly equal to the f divergence. Okay, so that's the result by Nguyen in 2016. Okay, by f divergence. How? So basically, what we will do now is we will look for the lower bound. Okay, and how we can get such lower bound. I think we are already on time. So I guess in the next class, what we will do is we will derive this. Okay, and once we derive a lower bound, this is a very generic template, or you can see this as a very generic template, and this will give us the GAN objective, where this will act like a generator, because I will because in general I don't know how to supremize, right? So I will choose a parametric function, which in our case is neural network. So I will say that this guy is a discriminator, and this guy is a generator with proper choice of t. So this guy will be let's say d phi, okay, which is trying to maximize the score, and this guy is trying to minimize the loss. So this is a very generic template. Okay, so with a choice of f, with a choice of t, it's in your hand. Okay, how do you parameterize these guys? Which choice of f you choose? What did GAN choose? Okay, and some changes in f could be used as a project also. Okay, so this is a very generic template for us. We will derive this, and specifically we will also derive GAN. Okay, so yeah, thank you.